Hi, everybody, and welcome again to Physics 10. Today is March 11th of the year 2021. Today, we're dealing with Chapter 9. However, I must tell you upfront that there is an issue with Zoom. So for those who are not in here live, I have been experiencing very big delays in terms of classes being delivered after they're supposed to be recorded. Right now, I'm looking at a class that happened yesterday at 9 a.m. It's still an ongoing. Basically, I did not receive the link for to download the class to upload it back for you guys to see it. Not their class, it's another class actually that I had yesterday in the morning. So, which means that there is a problem. Now, those who are not live, they will suffer from this problem. So hopefully you guys, I'm gonna try to send a message later on. Hopefully this recording will be available, because what happened is there was another class this morning also. I still did not receive its link. But for some reason, there was a class after that one that I was able to download and post for on campus. So I'm just experiencing problems with Zoom. So I'm going to try to have this available for you guys, hopefully tonight. If not, I would strongly suggest that you guys subscribe to the YouTube channel, because you will have a first take at it. The minute the video is available, you guys will access it and then basically expediting. The only thing I say in there is that you have to watch, because I upload a lot of stuff to YouTube from my other classes. And it will be basically, if you're trying to navigate which one your class, you will have a problem. So what you do in this case is look for the first two, basically the first word in the title of the video. For your class, it's going to say PHY10. So if you see anything other than PHY10, ignore it. That's not your class. If you see that the one that starts with this, basically your class name, you know exactly that that video is for your class, so you can basically watch it. If you didn't watch it, there are assignments for all of these classes, so you need to really, if you are not live, and there is quite a few of you who are not here right now, you really need to watch those to complete your assignment. So that's basically the deal in here. Again, I will try to, hopefully I will get this video, if your class is lucky enough to get the video again posted on time. But if not, I will try to send a message later on to everybody who is not here, since there's a lot of you. Anyway, today is on Chapter 9, and Chapter 9 deals with basically the law of gravity, of how Mr. Newton basically came up with it. So let me share with you the screen. Okay, so basically we're dealing with Newtonian synthesis. Before Mr. Newton, people basically, they wanted to understand motion, they wanted to understand forces, and they wanted to understand what's going on in the sky in terms of those objects that move in the sky. They divided the star into two classifications, basically. The stars that are fixed in the sky, that don't move year-round. So basically, if you look at the sky, for example, first of all, a star, there is one star that doesn't move at all. It seems like it's permanently in its position, and that is Polaris. And there are other stars in the sky that seem to come back in the same location year-round. They don't move. They're part of a constellation. Basically, a constellation is a group of stars that make a shape, and then basically we associate those stars. For example, take any star you want, Rigel, Polaris. I mean, Polaris is an exception because it's fixed almost all the time. Betelgeuse, whatever you can think of in terms of star, Antares, whatever you can think of in terms of stars, those stars are fixed in the sky. So we call them stars. But there is another another classification of stars that seem to hop from location to location every day, basically every week. You can see them move around in the sky, unlike the others, okay? So those were called planets, which really mean moving star, okay? Unlike traveling stars, that's probably a better description of what the word planets means. So they are still stars, except that they have this this behavior that is different than the other kinds of stars, and we call them traveling stars. So, and we knew at least about at that time 4 of them. Okay, we knew about 2 of them that seem to have this specific. One of them, Mercury, namely, that seemed to be either just after the sun goes down or just before the sunrise. So Mercury seems to be a companion to the sun, always following the sun before or after. So we knew about it. We also knew about Venus, which has a similar behavior also, although it's delayed a little bit compared to Mars. I mean, compared to Venus. Venus stays a little longer in the night, I mean, in the evening, and rises a little before. So there is, or at least if it rises a little before. So there is a delay between this motion compared to the sun and the, that's why Venus, which is the brightest object after the moon and the sun, first of all, is by itself during daytime, but the brightest object in the sky that you can ever look at is Venus. And because of its brightness and basically super intensity, it has a name. They call it the morning star or the evening star, depending on the time when it comes. So that was a star, basically, that really fascinated a lot of people. And then there was another star, basically, that was reddish in color. And that star, of course, again, we call that planet because it travels too. So that planet, namely Mars, that Mars actually stays longer in the sky and moves around from east to west and basically does all kinds of things, basically, during the night sky. So one time you find it in here, tomorrow you find it, actually Mars does something weird. It goes back in its path and moves forward. So it dances all over the sky. And then there was actually another, did I say 4? I said 5, I meant 5, okay. We knew about 5 stars at that time that travel. So the other one was Jupiter, of course, which is a big object in the sky too, but it's not as bright as Venus, for example. But that too seems to be moving, but at a lot slower pace than Mars, for example, okay? But it jumps and hops around, and month to month you can track it down. Okay, same thing with Saturn. Saturn actually was also a big object in the sky, not as big as Jupiter, certainly not as bright as Venus, but it's still a big object out there. So those are the basically 5 stars that seem to travel. We call them planets because they move around. At that time, we didn't know anything about Uranus and Neptune, but that's basically how we ended up with this many 5 planets, okay? We call them planets, meaning traveling stars. But something was weird about those objects because they seem to all move around the Earth, okay? And people were fascinated by their motion, in addition to the sun and, of course, the moon. So people basically came up with divided the month into several weeks and so on and so forth. But the week itself was divided into 7 days because every day was allocated to a specific one of these objects. You have the moon day, the day of the moon, namely Monday. You have the day of, what is it? Tuesday. That is the day of Mars, actually. I mean, if you look at the mythology, there is something that has to do with Mars there. Actually, in French and probably also in Spanish, the first 3 letters are actually referring to Mars, mardi in French. And I'm not going to attempt to say it in Spanish, but probably some of you probably have that background. You may know it in Spanish too, so it's similar to it. Then you have Wednesday, which is really the day also of Mercury. Okay, again, in French and probably in Spanish too, and Latin languages, they have the same starting words for it. In French, we call it mercredi. So that's basically also similar to probably Spanish and Italian and all of the other Latin languages. And also, and Portuguese also. And then you have the day of Jupiter, which is also Thursday. And then the day of Friday, which is the day actually of Venus. And then, of course, you have the day of Saturn on Saturday, and then the day of the sun, which is Sunday. So that's basically how we came up with this day. So it really influenced our culture. It influenced our basically everything that we do, not only just on a daily basis, but also our what we do in our lives, the economy, basically growing crop, predicting when these planets come back so that we do stuff, and the moon especially, and things like this. So when is going to be the next harvest time? When are we going to expect the next flood to come, and so on and so forth. So we needed to keep track of these things. So astronomy was a really major player when it comes to science in general, especially physics, because without it, probably we would not have Newton's laws of motion, and we would not have any understanding of what's going on. So that's basically where we were at that time. how the objects move in the sky was really fascinating. So we knew, I mean, if you go outside tonight and look at the sky, you will see them moving around the Earth. So the Earth seems to be the center of the universe. The Earth was believed to be the center of everything because everything revolves around the Earth. This was true until Mr. Copernicus came in and he analyzed, because at that time people were relying on Ptolemy's basically a calendar that he calculated based on the motion of the moon and the earth, or basically the sun around the earth and so on and so forth, the calendar, and he was able to predict when the next, for example, Christmas is going to happen, when the next Easter is going to happen, and all of that. So the church relied on his measurements to do, for example, planning for next season and so on and so forth. That was in the beginning of the 20th century, the beginning of the 20th century, the beginning of the millennium, the year basically immediately after the church got hold of the basically the land there. Now, move few hundred years back in the forward, about 1,400 years after that, there was a problem with the calendar that Ptolemy put it together. One problem was, for example, Christmas was not happening in Christmas, was not happening in the winter. It was happening somewhere in the spring, and Easter not in its proper time. It's somewhere in the summer. So things start to move around. So the church actually hired Mr. Copernicus to fix the calendar and come up with a better calendar. One of the things that he came up with was that the calendar was based on wrong assumptions, that the Earth is not really actually the center of everything. The sun is. All of these objects I mentioned before, he said, namely those 5 basically planets plus the moon, are actually not moving around the Earth, but they are moving around the sun. That's why it's called the Copernican revolution. It's really a big change in perspective. I mean, if you and I, especially if I go outside, I mean, it looks obvious to me that everything is moving around the Earth. So why in the world do I have to believe that things are moving around the sun? But again, if you look at the data, there was no doubt about it, that everything is actually going around the sun. That idea stood for a long time, of course, until about a few years after he published his work, another astronomer basically came into play based on observation again. All of this was with the naked eye. They did not have any equipment to look at these objects. They did not have telescopes, for example. Tycho Brahe came in and basically he documented, and he was very, very meticulous with his observations, especially about Mars and all of these planets. And he was able to track Mars when it goes back in its motion and forward and so on and so forth. And then he presented his work before he passed away to Mr. Kepler. And Mr. Kepler, after Tycho Brahe passed away, took that data and he came up with 3 laws. First of all, indeed, all of these objects revolve around the sun, including the Earth, which is another planet, no more, no less. And second, their path, actually, it's still first, the path that they go for on it is an elliptical path. And third, I mean, second idea in here, so it's still the first law, that the orbits are actually ellipses. And then the second point is that they sweep equal areas with equal times. So as they go around, they speed up when they're close from the sun, and they slow down when they are actually away from the sun. So when they're going like this, not circular, but rather basically an ellipse. An ellipse has 2 focal points that the objects can go around them, so that the distance between the 2 focal points is constant. So that was the second law of Kepler. Then he was puzzled with something that bothered him some. That is, how come, for example, some planets travel less time around the sun? Like, for example, Mercury takes the least time to go around the sun, whereas some other objects, like, for example, Saturn, takes a long time to go around the sun. And it seems like Mercury, according to the calculations, is a lot closer to the sun versus that of Saturn, and actually all the planets in between them. So that puzzled him, and of course he looked very closely to Mars again, because he had ample data on it, and he came up with a third law that says basically the time squared, basically 1 year for the Earth, it's more than a year, almost 2 years on Mars, squared. You square that number and divided by the distance, the average distance cubed is a constant number. So he came up with these 3 laws, and that was great. That was toward the beginning of the 1600s, the 17th century. And of course, Galileo, just before that, he looked at I mean, after that, actually, he looked at the, he took the toy that people used to play with, the telescope. He did not really invent the telescope, but he took that toy, modified it, and looked at, because there was a lot of criticism for Kepler and for actually Copernicus too, and looked at, because there was a belief that, look, the heavens are, and this was borrowed from the Greeks, by the way, not from the church itself, but the church adopted that idea, is that, look, the earth is not perfect because men sinned on it, okay? But the skies, the heavens basically are perfect. There is nothing more perfect than a circular path. Therefore, all the planets must orbit circles. So that's one idea. Not only that, but they orbit the earth. Mr. Galileo, when he took that toy and pointed it to, for example, Jupiter, he saw one thing. And that is, he saw the first night, it's actually 3 moons going around Jupiter. And then the next night, he saw the 4th moon. Of course, we know them today. They are Io, Europa, Ganymede, and Callisto. Okay, those are called now they call them the Galilean basically system, because Galileo is the one who basically observed them first. So they don't revolve around the Earth. These are 4 objects in the sky. They revolve around Jupiter. So this idea that everything must revolve around the Earth and we are the center of everything is not true. Furthermore, when he looked at the moon, he saw that the moon has some valleys and also mountains and peaks and everything. So this feature that you're saying it has to do with the man sitting on Earth and all of that is not necessarily true, because here is the moon in the heavens and it has the same features. So he supported a lot of the work of Copernicus and also of Galileo with evidence, with observation. Okay, for that he paid for it dearly. Anyway, Mr. Newton came way after, actually after Mr. Galileo passed away, and he was a student. He came up already with 3 laws of motion. And when the plague hit London, just like what we are right now, basically, or are under the same conditions as that, students were sent home, and he was sent home. And he was handed actually the work of Kepler, and he was told, can you explain that? Can you come up with an explanation of why all of these planets, including Earth, according to Mr. Kepler, go around the sun in these elliptical orbits, number 1. Number 2, they sweep areas at constant rate, number 2. Number 3 is they seem to have the time it takes for them to go around the sun once. That time, if you square it and you take the distance from the planets to the sun and you cube that number, the ratio is always the same. Whether you take Mercury, whether you take Venus, whether you take the Earth, whether you take Mars, whether you take Jupiter, whether you take Saturn, it's the same number. It doesn't change at all. So why is that? What's the secret behind that? Of course, Mr. Newton was in the countryside and he thought about the problem. And this is basically what he's thought about. And this is a big, big deal, okay? This is what he said. Forget about that for right now, okay? I think what's going on there is the same reason that the moon is going around the Earth. Why in the world the moon goes around the Earth once in every lunar month, which is about a solar month, okay? So it seems like, to me, he was thinking, what causes all of these planets to go around the sun is the same thing that causes the moon to go around the Earth. That's one thing. Furthermore, if I take an apple and drop it on the Earth, that seems to be the same reason the moon is actually going around the Earth. The moon is going around the Earth, not because of anything. It's trying to fall to the Earth, but it has a big speed. And that speed is preventing it from falling toward the Earth, basically. In other words, if I take this apple and throw it as fast as I can, it's going to be in orbit around the Earth. So the same force that causes the apple to fall toward the Earth must be the same apple that is actually keeping the moon from flying away, because according to his first law of motion, if the moon is not under a force, it should fly away, it should continue straight and never come back. But yet it's in here, it's held in place, so there must be a force, and that force must be this very same force that causes the apple to fall toward the ground. Now, that force also must be holding the planets toward the sun. So he took an idea about an apple that you can actually do in your lab and work with it. And Mr. Galileo answered that question, by the way. He already gave him the acceleration for the apple toward the Earth. So he knew about the work of Galileo. As a matter of fact, his first law is just the work of Mr. Galileo. And he was able to deduce what causes these planets to go around the sun. And that's why the word in here is universal. So he took an idea that we see on a daily basis in our lives and made it into a law that governs the universe, okay? He extended it, okay? So the universal law of gravitation. So it's the same thing that causes the apple to fall toward the Earth, okay? It's the same thing that causes the moon to fall toward the Earth. Actually, the moon is falling. The only reason why it's not coming down actually anytime soon is because moving this way, that's all, okay? The apple doesn't have this speed, so it's gonna fall straight out. So this force is the same. And that is actually what is keeping also the planets to go around the sun, okay? I have 4, 5. So this is Mercury, this is Venus, this is the Earth, this is Mars, this is Jupiter, and this is Saturn, okay? So that's basically the same force. And the only reason, again, why they are not falling is for the same reason. Like the moon is not falling in here because they have a velocity, and that's it. So that was his really biggest contribution. I mean, he sat on this work for about, what, 4 years before he published it, because there was a problem. The problem has to do with the apple, actually. Because the distance to the Earth to the moon was known to be about 384,000 kilometers. Okay, so he knows how to calculate that number. But he was basically trying to argue that the distance between the apple and the Earth is not about 1 meter or 2. When you drop the apple, it's about 1 meter, but rather it's the radius of the Earth. Okay, and that is about 3,600 kilometers. And that has to do with the radius of the Earth. So as if the entire Earth is pointed inside its own center. And that must be the same thing also for the sun. For that, he had to invent another branch of mathematics called calculus. But that is, in a nutshell, basically the whole thing in here. So his work was really the foundation for a lot of these things that we know now in physics and things like that. And it's all coming from astronomy. Now, this was all good and fine. If that's all there is to it, there is no problem with it. However, I mean, it's not good, actually, honestly, to be honest with you, if you can only explain something. You can't, it's not satisfying to just explain things. Explaining things is not what scientists do. If all you can do is explain how these planets go around the moon and then basically describe the first law of Kepler, the second law of Kepler, and the third law of Kepler, then anything will do. Any explanation you can come up with is good enough. I can tell you, for example, I have another explanation to this, and physicists use this example a lot. As a matter of fact, I see, or I believe, there are little angels pushing these planets to go around the sun in such a way that this orbit, so the angels are making sure that these orbits are actually elliptical. These angels are making sure that these planets, when they are near the sun, they speed up, and then when they are further away from it, they slow down. And these angels also are making sure that the time it takes for them, divided the time squared, of course, to get around the sun once, divided by the distance cubed, is constant. This is as good as Newton's explanation. There is no problem with this explanation whatsoever. So you can think of any kind of scenario that you would want to, okay? You ask me, okay, what are the angels, or how big they are? What's their color? How many wings do they have? I tell you, that is my problem. I tell you, part of the problem in here, part of my theory is that you cannot see the angels. Okay? So stop asking these questions, basically. So that's my theory. That's how I think this thing is working. So there is no reason for it not to be that way. However, Mr. Newton does something that I can do with my theory. He actually found that constant, okay? He found that constant, the ratio of the time squared for the planet to go around the sun divided by the average distance for it. He did not just find it as a constant, but he found what it really is. That I cannot do it with my theory. Not only that, but when a comet came visiting the Earth at that time, around the Earth in the skies, Halley looked at it, basically timed for 1 week how long it moved actually in the arc sky, and predicted 76 from today is going to reappear. Sure enough, within a day or two at most, 76 years later, it came back. I cannot do that with my theory. And that is the power of science. So as a scientist, not only you explain things, but you predict things. You come up with the new results that your theory does not just explain what has been observed already. It goes a step beyond that. And this is the power of physics in here. That I cannot do with my theory of the angels and you cannot see them and all of that. Of course, that's nonsense. This is the why physics is important, and this is what scientists should be able to do. If all you do is explain what has been seen already, what has been observed already, that is not good enough. You have to predict something. And this is exactly what Mr. Newton did. He went a step beyond what Mr. Kepler have seen and observed. He found that constant. It's not just any constant. It has to do with the mass of the sun, actually, that constant. And that's why, if you take those numbers now and you apply them to the moons of Jupiter, you're going to find the mass of Jupiter instead of that. That's why the moon is in there, is because of the mass of the Earth, not because of anything else, okay? So again, that constant has to do with the central object with which everything revolves around. So that is an important thing that Mr. Kepler, first of all, never observed. He just saw it's a number constant, that's it. And I can never come up with my theory. Whatever theory I invent, there is no way for me to come up with that number or that explanation for it. It goes beyond the observation, okay? Sure enough, if I take that theory now of Mr. Newton applied to Jupiter, for example, we were able to measure the mass of Jupiter or any other object, for Saturn too. That's how you can measure its mass, by just looking at its moons and how they go around it. Now you have weighed Saturn, okay? So that is basically the power of this thing and how you can come up with stuff. Obviously, Halley's Comet was also another one of the prediction, one of the things that really made this thing into a success. The discovery of Neptune itself as another planet was relying on the work of Mr. Newton. When people looked at the motion of Uranus was discovered later on, actually by accident, doing other things. But when we looked at the motion of Uranus and we looked at the motion of Saturn, we two independent astronomers, basically, when they did the calculations, one in England, one in France, they said, look, there must be a planet out there, and this is its mass, and it's out there. And they pointed exactly to a specific point in the sky. Sure enough, when they turned the telescope, they found Neptune, based on this theory. Because Neptune is so far away, you cannot see it basically with the naked eye. You have to have a telescope, and you have to know what it is to find it, because it's so faint compared to the others, okay? But that basically tells you how this powerful stuff is, okay? Anyway, the legend has it that Mr. Newton was sitting under a tree and an apple fell on his head, and then all of a sudden he said that, look, F equals to a constant times M1 times M2 divided by R squared. That is a legend. There was a lot of thinking for coming up with this relationship, okay? It's not true. It's not like it fell on his head. Try as I might, if I go and sit under a tree, and I think the only thing I will get from the falling apples on my head are bumps on my head, that's all. I will never be able to get this one. Nobody is, not even Mr. Newton himself. So what the thinking was, look, the weight of the apple is equal to the mass of the apple times the number that Mr. Galileo has found, okay? He thought, look, if I am a worm now sitting on a planet Apple, tiny creature living on a planet Apple, from my vantage point, it's actually the Earth that is falling on me. So if you take an apple and have something living on it, when he looks up, he's going to see the Earth, and the Earth is coming rushing to it. He said this force must be also not only proportional to the mass of the apple, but also proportional to the mass of the Earth. And then he knew about the value of G, which is 9.8 that Mr. Galileo has measured already. And then the distance from the apple to the Earth is around 3,600, as I said before. And the distance from the Earth to the moon was known around 384,000 kilometers. The ratio of these two numbers is about 60. He took this G for the Earth, and he can find G that the acceleration of the moon. It has to do with how fast it goes around basically the Earth, which is what, 1 lunar month basically, goes once around the Earth. So he can tell that, and he has the distance, has the time, he has the distance, he can find the velocity, and he can find the acceleration, and we're back in business. So he can compare the two accelerations, and he found that the acceleration of the moon is basically 1/60th squared basically of this number. So he knew that this distance now has to do with this law. This force must be inversely proportional to the square of the distance. As you move away, the force drops by 1/, distance squared. Obviously, he had a problem because the mass is in kilogram, another mass is in kilogram, and the distance is in meter squared. This doesn't fit the bill for a force. So he needed to fix the units. That's why he introduced this number. Not only that, but he needs to recover the value of Mr. Galileo that he found 9.8 for the apple. So if you plug in the mass of the Earth, the mass of the apple, and the radius of the Earth, this whole thing must be just the mass of the apple times the G, which is 9.8. So from there, he deducted the value of G, big G, the constant in here, as being 6.67, a very, very tiny number, 10 to the negative 11, okay? And it has the proper units of Newton per kilograms squared, meter squared. So basically, he had to fix the units with G, and he has to fix also the value of little g. So that's basically how he came up with that. So it's not like it fell on his head and he came up with that law. That was a big, really, discovery. So this is what we meant by synthesis, okay? So this is when he came up with this whole argument about this, that. So he was looking at the apple and looking at the Earth and said that what causes the apple to fall from the tree must be the same force that causes the moon to fall around the Earth. The only reason why it's not falling actually is because it has that velocity, hence by the first law. Because if it was by the second law, it's going to fall in this way. Okay. So there was a force, but it has a velocity in here. So if this force did not exist, the moon should never stay. It's going to go forever and ever and continue in the same direction everywhere, all the time. So we'll never see it again. We'll see it just the first time around, and that's it. And after the force is canceled. So there must be a force, and that force is exactly the same thing that caused this apple to fall. So that is basically his reasoning, okay? Obviously, he was in the country at that time, country, and there was a lot of apple trees there, but that's basically how we argued that. So motion of stellar planets was natural, not governed by the same. So people believe that these things have nothing to do with anything else. It was Newton who recognized that the force directed toward the sun must act on planets. This is similar to force that exerts on an apple that falls towards it, okay? So this is basically the synthesis. The same set of laws apply to both celestial and terrestrial objects. Okay, so isn't this fascinating? That here on Earth, we're talking about laws and G and acceleration and M equal to MA and all of that. And based on all of this argument, we believe the same thing if we go to any planet in the universe. On the other side of the universe, the same laws that we're talking about exist there too. So if we were to conduct these laws somewhere else, it's the same laws. That is really what his main thing in here is. Again, Law of universal gravitation, everything pulls on everything else. So that this force must be pulling all the time. It's an attractive force, okay? Force of attraction. And why is there everybody in here? It's just because of typo. Okay. No, it meant everybody, not everybody, not we and you and I. It's every system, if you wish, okay? Every object. Probably more appropriate to say every object. Okay, attracts every other object. Okay, with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance that separate them. Okay, this is how we write it symbolically. The curly here, this wiggle in here means proportional. It doesn't mean equal. It means it goes as the others go. Okay, if you double this mass, this force doubles. If instead you double this mass, this force still doubles. If you double this distance, this force shrinks by a factor of 4. Okay? Again, if you triple this mass, the force triples. If you triple this mass instead, this force triples. If you triple the distance, if you go 3 times as far, this force drops by a factor of 9 from what it was before. That is what this thing means. Symbolically, we write it m1 times m2 divided by d squared, and on the other side is f. This is not an equality for 2 reasons. First of all, it's not going to give me the proper force if I apply it to an apple, for example, or my weight, for example, any object that Mr. Galileo has already measured at that time. Okay, so it's not going to apply. It's not going to give me the numerical value. So I weigh 700 Newton. If I were to use this formula between me and the Earth, it's not going to work. It's going to give me some nonsense numbers in here. So it's not going to give me 700. That's one problem with it. The other problem also, the units don't match. Okay, remember the weight, which is the force in this case, must be the mass, which is in kilogram, times g, and g is in meter per second squared. So these are the units I need for the force. This is clearly not that. This is in a kilogram. The other one is in a kilogram, and the distance is in meter when you square it. So this guy, this product on this side, is in a kilogram squared divided by meter squared. It's not anywhere near a kilogram meter per second squared. So we needed actually a constant in here to fix this business. So we needed that big G. And that big G does few things for you. First of all, my weight will become all of a sudden back to 700 Newton, number one. Number two, also the units are proper. The units become back into kilogram meter per second, okay? So this is how this whole argument was. So the greater the mass M1 and M2 of 2 bodies, the greater the force of attraction between them, the greater the distance of separation to the D, the weaker the force. It's not just weaker, but it goes by power law, square actually, okay? So Newton's most celebrated synthesis was and is of earthly and heavenly laws. Okay. So this is really, of course, it was a time of like, it took 2 years from the time of the pandemic there for them to go back to school. And it seems like we're on the same path, at least so far. It looks like we have been a year now since the pandemic started. Actually, a little over than that, because of the fact it started in December of 2019. And we're headed toward the fall of 2021. So there are a lot of parallels with that. Hopefully one of you guys will invent something, because he was a student like you guys too. So he was not actually professor or anything like that. So, okay. He's got so many famous stuff in him with his stories. He was a quiet man. He didn't talk too much. And he did work not just in this field. He did also in optics. He did also in telescopes, actually. He modified the telescope instead of using the refractive telescope, he used actually a reflective telescope, and now it's known as the Newtonian telescopes. And he did a lot of work in other fields too, okay? And invented actually the branch of mathematics called calculus. So he did quite a few things, okay? Anyway, so the gravity is the weakest of 4 known fundamental forces. There are 4 known fundamental forces. There is gravity. This is weak, actually super weak, extremely weak. And then we're talking about electricity and magnetism, electromagnetic force. Okay, this is super strong. And then we have the weak force, the weak nuclear force. The weak nuclear force and the electromagnetic force, they are very similar in strength, but we have even a stronger one of them both. It's called the strong nuclear force. So this is actually the force that binds the nucleus together. So those are the fundamental forces. There are 4 of them, okay? And gravity is one of them, but it's the weakest of them all. Yet it is the one that holds and glues the entire universe together. Why? Because all matter is neutral. So the electromagnetic forces, they cancel one another. Okay? They're important, but they cancel one another, at least on a large scale. On a small scale, on the atom scale, for example, they are important. That's what keeps the atom together. If you take, for example, salt, which is sodium chloride, the only reason why you have salt is because the chlorine, in this case, grabs the electron of sodium and puts it next to it. Now this becomes negatively charged, this becomes positively charged, and now you have 2 ions. One of them is positive and the other one is negative. So the electrostatic force, now electromagnetic force, pull them next to one another, and now you have salt, okay? You have NaCl. So on the atomic level or molecular level, electricity and magnetism play a major role, okay? On even smaller scale, on the nucleus, they play a major role too. I mean, the other 2 forces too. Now, on a large scale, like for example, on the galaxy size or super galaxy, I mean, a cluster of galaxies or super cluster of galaxies, or the of the universe, this forces, they basically, it's just basically gravity, albeit it's super weak. If you're wondering how weak it is, it's unimaginably weak. Okay, something that is of tremendous size. If the gravity is 1 Newton, for example, in strength, this electromagnetic force would be 1 followed by, I should have put 0 here first. What is this? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. See how many zeros after the 1? 40 0. 10 to the power 40 times. I cannot even read this number. I don't know if anybody can read it, because it's not a billion. Billion is up to here. It's not trillion. Trillion is up to here. Quadrillion or something is up to here. But this is a number that is so big. That's how big this next level force is compared to this guy. So that's why I try to put a big gap in here, okay, between them. Anyway, so this G here is just this number. And again, it was needed to fix 2 things, the units and also the value of G for on Earth. This is big G, so that we fix little g, and little g was actually measured by big G himself, Mr. Galileo, okay? So that is basically the story of the whole thing. Once the value was known, the mass of the Earth was calculated as so. I mean, you can measure the mass of the Earth just by looking at the moon, for example, or an apple. So basically, this G now is related to if you're curious trying to find the mass of the Earth, it's going to be G that Mr. Galileo has measured, which is G times the mass of the Earth divided by the radius of the Earth squared. Radius of the Earth squared is 6,400 kilometers. Basically, you have to convert to meters. G, you know what the value is. G is 9.8. From here, you can find the mass of the Earth. So that's how you weigh the Earth. That's how you can weigh it. Okay. So the universal constant, which links the force to mass and distance, is just like another constant. Okay. So it's not like little g. Little g changes from location to location on Earth. So it's not the same thing. Acceleration due to gravity, that is actually the same thing as that one. Speed of uniform motion, for example, when you put your cruise control, that is not fixed because you can change it later on and change to a speed control. So it's like pi, it's just a fixed number. This is how we happen to be in this universe. 6.67 times 10 to the negative 11. Again, it's a Newton meter squared per kilogram squared. So this is basically the constant, the universal constant in this universe. People were fascinated by this inverse square, 1 over distance squared. It's just like basically the light bulb. If you put a light bulb somewhere and then you move away from it, light starts to dim. And as you move further and further and further away from it, light gets dimmer and dimmer and dimmer. And that actually follows a square law because of the fact that as you move away, the light that was covering this small area now has spread over a bigger area. And the area is proportional to the square of the radius. Therefore, the light now spread over a big area, and that's why you see dimmer and dimmer. It's like your cell phone. When you're close from the tower, you have so many bars. When you move away from it, the bars drop, and they drop also according to 1 over square law. So it seems like this square law has to do with the geometry that we live in. But that's exactly how this thing is. Not only that is true here, but it's true also for the other force that I mentioned in here. This one. And we will see that when we do electricity. That too has 1 over distance squared. Actually, as a matter of fact, one of the other two also has it too, but except it has some corrections in it too. But that is a peculiar thing that seems to suggest that there is some universality. The only trouble with that, and we will see that down the road, is gravity actually, let's leave it as is for right now, okay? So when we come to relativity, we're going to revisit this idea. Because there is an issue there, okay, with this inverse square law. Okay. So again, this is what I was talking about in here. Can of paint, when you spread it, right now it's tense if you bring it very close, but if you move away, now it's spread through a big area. Same thing with so it's a lot lighter at the end, okay? So again, 4 area units, so it drops by 4. And here you have how many? 3 by 3, that's 9. So it's going to drop by 9. And you have here 4 by 4, it's going to drop by 6. Because the distance went from 1 unit to 2 units, then the area in this case is proportional to r squared. As a matter of fact, the area of a sphere is 4 pi r squared. So as r doubles, the area quadruples. As the distance triples, the area in this case goes by a factor of 9. As the distance goes by a factor of 4, the area goes by a factor of 16, and so on and so forth, okay? So that is basically how this works. Again, this is how the square law in here. It never goes to 0 though. Even though the distance goes so huge, you're going to be dividing by a big number, which makes it a very small thing. So it doesn't mean that you are going to get away from the gravity of the Earth. If you are very close from the Earth, your gravity is actually your weight. I mean, the force in this case is your weight. But as you move away from the Earth, your weight starts to be less and less because of that 1 over distance squared again. It's going to be your mass times the mass of the Earth times that g, and that is the force of gravity in this case as you move away from the Earth. But because this distance grows and grows bigger and bigger, then this force becomes weaker and weaker. As a matter of fact, it approaches 0, almost 0, but not quite. It will never get 0. So how can you escape the pull of the Earth? Never. I mean, you will be at some point that it will be so negligible, you're going to forget about it. Maybe you are closer from another planet like Mars, for example, then you will feel more Mars than you feel Earth. But did you actually escape Earth? No, you still have influence of the Earth wherever you are, okay? Like that thing that never goes away. It will never go away. Actually, it's not just for the Earth. We are under the influence of everything else in the universe, from the furthest point in the universe up to this point, but they're actually faint. The only thing that dominates our weight is actually the Earth right now because we're close from it, okay? We're still being attracted by everything else, including Mars and Jupiter and the Sun and Ceres and Pluto and whatever you might think of out there, okay? The Himalayas and everything else, okay? So the force of gravity between two planets depends on masses and the distance apart. Planetary atmosphere, that is nonsense. Rotational motion, no. All of the above, no. This is the only one that matters. Okay. Again, this is talking about when you double the distance, and if the two masses double, if you double one and you double the other in the same time, the whole force, of course, will quadruple because you're multiplying by 2 and then 2. Okay. If the mass of one planet is somehow doubled, the force of gravity between it and then its neighboring is just doubles in this case. That's it. If you double both of them, it's going to quadruple. But if you double one of them, it's going to just to double. So weight, force on object exerts supporting against a supporting surface. Again, this is basically, do I feel my weight or not? That is the question, okay? Here is the problem. If I am standing on anything, it doesn't matter what that is, okay? This is me, okay? Then I am exerting a force coming from the weight that I have on that surface, okay? Now, the surface itself exerts a force back on me. If I'm not moving up and down, if I'm not jumping up and down, or if this surface is not moving up and down, accelerating up or down, I should say, then in this case, I should feel this N, the normal in this case, the support force, exactly like my weight. So that is what I feel my weight. Case in point, if I'm suspended in the air, okay, not held by anything, just basically free, okay? Let go, for example, okay? You go on a plane and you jump, okay? Don't do this experiment. It's going to harm you at the end of the day. But if you jump during that time, you don't have any support force. You don't feel your weight. You feel weightless. You still have weight? Absolutely. Do you feel it? No, because what you feel is actually the support force, okay? So weightlessness, no support force as in free fall, okay? So astronauts, they feel weightlessness because of the fact. So it's a feeling more than actual loss of, so this is actually misleading. It might suggest that you lost your weight. No, the weight is still there. The force of pull of gravity is still there. Here is the example that we always illustrate. So if you're standing on an elevator and the elevator is not accelerating up or down, meaning it's moving either at constant speed or a stationary, not moving at all, then in this case, the scale, which really reads the support force, is exactly what you're supposed to have in weight. End of the story. Now, if somehow the accelerator takes off, in this case, you're going to feel, you're going to press with the weight, W, plus because of your inertia now is going to be your weight times the acceleration. So this is going to also push against the scale. The scale now is going to push back harder, more, to compensate for this additional force that is coming from your inertia. So in this case, you feel heavy because the scale is push heavy, and actually if you read down, you're going to read a higher number. So if you used to weigh, for example, in pounds, let's say, for example, 160 pounds, you look down, now all of a sudden you're 167 pounds, okay? Did you eat anything? No. Did you carry anything? No, it's still the same thing. But the mere fact that you're accelerating, you feel heaven. Actually, you feel it too. It's not like it's not like a reading number. It's not like something happening in your head. Actually, you feel it too. okay? So that is not something you imagine, okay? So you don't need to go to seek help for it, okay? You don't need to pay a professional to tell you that you're not, it's not something imagining, it's really real, okay? On the opposite side of the coin, if you're accelerating down, so you're still pushing with your weight, but your inertia is pointing up now because, again, it wants to stay in its up position. So now your overall force with which you're pushing on the floor is less. It's your weight minus this inertia, this mass times acceleration. So this is the acceleration. MA is your acceleration, okay? So now when you're pressing less on the scale, you feel lighter. If you look down, actually the number instead of 160 all of a sudden is 153. Don't celebrate. You didn't lose any weight. The only thing is just a feel for it. That's all. Okay. So it's the opposite of the other one. So you don't go and getting anything. So it's the same thing. Okay. It's in the opposite direction. Case in point, if somehow you cut the string in here, now in this case, your weight is still pulling you down, but the acceleration now is exactly g. So in this case, your inertia is going to be mg, which is actually your weight too. So now you're not pressing with anything on the scale, and the scale is not pressing anything, and you feel free. You feel weightless, completely weightless. Make sense to you guys?
Yeah, makes sense.
Okay. So this is basically, okay. So an elevator accelerates upward, your weight reading on a scale is because, again, when it's accelerating upward, so this is its upward acceleration, your inertia, which doesn't like to change your motion, keeps you in the opposite direction. So this is your inertia. Your weight is mg, so your apparent weight is mg plus a. So you feel, because now the scale has to push not against just your weight, but against the other one. So it feels heavier. So your weight reading on a scale is greater because you're pushing more on the scale and the scale will push back more, okay? Obviously, if the scale is not strong enough, it might break, but that's another story. We're assuming the scale is rigid enough for it not to break. So when escalator accelerates downward, your weight then is going to be the opposite now, okay? So it is accelerating downward, okay? So the acceleration is down. Your inertia is going to be pointing up. Your weight is still mg in here. So if you take the force with which you press is the difference between the two, which is mg minus a. And of course, you're going to feel less now. Okay? You're going to feel less weight because you're pressing with less force on the scale, and the scale will respond in kind to you by giving you a feel that you're really your weight is less, and actually you feel less. You feel you weigh less. Okay, so it's not something you imagine again. So when the elevator cable breaks, then in this case you're going to have 0 reading, okay, on the scale. What is it? The question? This one. Okay, so this is 0 reading on the scale. Okay. So again, this is just basically a repetition of this whole argument in here. Again, the motion of the Earth, basically the moon and the Earth had another thing that we basically associate with the Earth and the moon, and that is the tides. The tides happen twice a day, and because of the fact that as the Earth spins around the axis, the moon on that day, motion is hardly moving from its location. So it moves once a month around the Earth, but that's once a month. We're talking about 24 hours now, period. 24 hours, period, the Earth spins around itself twice. So here is the deal. This portion of the Earth, which is the ocean on this side, is closer to the moon than this portion of the Earth, okay, on this side. So it's pulling more on it, okay? Since it's pulling more on it, it's going to be a high tide in this case. Not only that, but the entire Earth is actually dislodged in the same process versus this amount which is left behind. So that's going to be high tide, but not as much as this one. So there are two high tides in the day. On this side, on the side facing me, and on the other side that is on the other side of the screen, that is actually a low tide in the same time, because the water is being pulled, stretched from both sides, and it's high tide on both sides, albeit one is bigger than the other, but it's high tides. And on the sides that are facing this way, it's a low tide, okay? And this thing spins, so the high tides and on both sides, they move around and they stay opposite to one another all the time. And at the same time, the low tides also, they spin while the others are spinning. That's why you have two tides, two high tides a day in 24-hour period of time. You have the one here, 12 hours later, this will move here, and this one will move here, okay? So that is basically what happens. So that's why you have two high tides. In the same time, you have also two low tides. And you can actually see it if you happen to be near the ocean. You see actually the tides rise. I was caught one time between the tides. I don't swim because I almost died when I was the age of 17. And I walked the beach. So one time I went this way in Del Mar Beach, actually in San Diego. When I came back, the tide was there. So I had to actually climb the Torrey Pines, the Gulf side, and go back to my car because I can swim. So you know something about me now. Okay. I know some of you probably you can do that. Now there are two kinds of also tides. The tide is can be due to the sun also plays a role. But the sun, albeit is a lot bigger, but it's further away, the sun can have help with the tides or can suppress them a little, okay? So when it helps them, when it's on the same side of the moon, basically, during the new moon or during the full moon, then in this case, basically it's more. So this is going to be pronounced. This is going to be more effect, hence the spring tides. But in the opposite in here, so the sun is actually pulling a little on the low tide side, so it's going to take it from the high tides where the moon has the biggest effect because it's closer than the sun. Okay, so again, this tidal motion has has a lot of things. It does friction with the oceans. It causes so many things in here, and it's the reason why the day on the Earth is actually slowing down because of this loss of energy. So there's a lot of things in here, okay, at motion. And I don't know if we're going to do astronomy in this stuff in here or not, but it has a lot of implications also on the moons, for example, of Jupiter and the moons of Saturn, because it's these things that the needing that is causing energy in those moons and causing oceans basically under their surfaces, like Europa, for example, and so on and so forth, okay? Again, gravitational fields, it's the interaction between the Earth and the moon is action at a distance. How do they interact? So basically, we want to understand this interaction. Okay, let's say, for example, does the Earth and the sun, or the Earth and the moon, do they send messengers between one another so that they know that they are? Let's say, for example, tomorrow, the sun is gone. How would the Earth know that the sun is not there anymore? Okay, or something happens to the sun. How would we know that? How would the Earth knows? Does the Earth calculate all the time? Okay, the sun is there. Let me find exactly where I need to be. The mass of the sun, my velocity, and all of that. It needs to do that, or how is it this going? So basically, the idea behind it in here is that whether the Earth is in there or not, it doesn't matter. The sun produces a field in this point, and that is how the Earth knows about the sun, because it's in that region. Okay. The same thing with the moon. How does the moon know the Earth is there? It doesn't communicate with the Earth on a regular basis and try to adjust its position every second while it's moving. The only way it knows about it is through this gravitational field. So this is the idea of fields, and it helps us understand this force at a distance. Again, wait later on when we get into relativity, because Mr. Einstein has a better, or at least, yeah, a better explanation for this. Because this force at a distance was a puzzling thing for even Newton himself when he proposed this idea. And the better the explanation that he came up with was this one. How do they really, they're not connected with tether or anything. So how do they communicate with one another? How do they know? Okay. And the idea came from Mr. Einstein that actually these fields are nothing but just a deformation in space-time continuum. And that is the general theory of relativity, which is a really different picture. It doesn't even involve forces at all. It just involves geometry. Okay. So again, we're talking about the field, and the field is an attractive force. So if you happen to put an apple in here, that apple will follow the field lines, okay, until it comes to the ground and basically attach to it, and that's it, okay? So, okay, we have to come up with something to talk about today. I know I didn't want to really honestly put a lot of questions because I'm having difficulty with the video. So some of you who are not live right now, they might not be able to get to the question in time. But basically, let's have this one as the item of discussion, and the only item of the day today is that describe how gravitational or gravity works. And basically the answer to it is through fields. That is how, and the Earth, for example, is aware of the presence of the sun. And that is how the moon is aware of the presence of the Earth. And that is actually how, too, the apple is aware of the Earth by the field that the Earth is creating around itself. There is a field in this point. There is a field in this point created by the Earth. If I take an object of this mass and put it there, this object now is subject to that field, and it's going to fall because of that, okay? So if I look at this point in front of me, this point exactly, there is actually something I cannot see with my eyes. That is the influence of the Earth in that point. So if I bring one object in here and put it in there, that object now is under force because of that field. If I let go of it, indeed it's going to fall. That is the picture that we have in here. That is the answer to the prompt, okay? So the way this force acts is by creating a field. Every mass creates a field around it. So the supergiant black hole that sits in the middle of the galaxy creates a field around it, attracting all of those stars next to it, closer from it. Those stars basically, and all of the black holes next to it, including the supergiant black hole, the Sagittarius A star, they create a field around them to attract more and more stars. And those stars, again, in addition to what is inside included, attract more and more stars. And that is how the Earth, the sun is actually maintained around the galaxy because of that field. Otherwise, there is no reason for it. So this is the galaxy in here. The distance from here to here is 100,000 light years. The distance from here to here is about what? Same thing, I guess. So, but the distance from here to here is about 10,000 light years. Okay, so huge, this 10,000 light years. It takes 10,000 light years, 2,000 years for light to go from end to end, just from the thickness. From end to end takes 100,000 years to go from end to end. The sun is here, some 30,000 light years from the center of the galaxy, 2/3 of the way, because this distance is about 50,000 years, 50,000 light years. So we are about 2/3 of the way in there from the sun, from the center of the galaxy. And because of this supergiant black hole in here, and because of the stars in here, and this bunch of stars, the sun is held in this place. Otherwise, if there is no force in here to keep these things together, the sun will leave the galaxy and go on its own in empty space. And you look at the sky and you see nothing. Faint, probably, galaxies out there. Okay, because most of the night what we see are actually the stars nearby. Okay, about 2,000 of them. So that's what we see on a given night outside, on a clear night. So again, that is basically also the same thing, because these things are creating fields around them. And that's what keeps the sun going around the center of the galaxy. And it's the same thing, whether we're talking about the galaxy or the apple in this case or anything, okay? Make sense for you guys?
Yep.
Yes, it makes sense.
Okay, very good. So again, this is what I was talking about in here. This field drops like 1 over distance squared outside, but grows with more and more matter inside. Because if you are right in here, there is nothing to attract you to the Earth. You can be zero, basically, attraction. But as you move further and further and further away, more and more stuff is attracting you, like the analogy I gave earlier with the galaxy, okay? And so this thing will attract you if you're sitting in here on the Earth. So it grows linearly, actually, up to the radius of the Earth. At that point, it starts to drop like 1 over distance squared. This is amazing, actually. This is the same thing in here for the galaxy. Okay. Vera Rubin, when she looked at the data, she expected this graph too. She expected, as she looks at the stars going around the galaxy, to grow linearly from the center of the galaxy and then start to drop. Like this, what happened to the Earth? Because if I look at the star here outside, just barely outside of the galaxy, so its attraction in here, its speed actually needs to slow down. Just like, for example, it takes almost 2 years for Mars to go around the sun because it's further away from the sun. And the acceleration of the apple is, what is it, 3,600 times greater than the acceleration of the moon, because the apple is closer to the Earth than that of the moon. So I expected this behavior because of these things. That's no problem. But what she actually found was surprising. She found, yes, it grows like this, but the stars that are here, sitting in here, they call it the halo of the galaxy. They didn't really drop. They continued like this. She was puzzled with it. She was really puzzled and scared initially, especially being a woman working in a field dominated by men. She didn't know what to do. She thought, okay, there seems to be more matter in the galaxy than I can see to account for this non-drop. And then when she published her work, of course, people, that's nonsense. It can't be correct. So they looked at it again, and she was right. The galaxy seems to contain something that was dubbed later on dark matter. She recounted her story. She passed away a few years back, but she basically was talking about how discovery of dark matter. So this stuff is big. Take it from basically this room right now. It's not just a small amount of dark matter. Apparently dark matter is dominant in the area where we are. It's far more than regular matter, than you and I. Okay? We don't know what it is. That's why we call it dark. It's not because it's black or anything like that, or dark in color or anything like that. We don't know what it is. We have no idea. Okay? So again, this is the Earth. So this is expected, okay? So the apple falls like 1 over distance squared. And don't tell me in here the dark matter. If there is dark matter, then it's another story. But that's basically what's going on in here, okay? So again, that same idea now, as you fall from the Earth, if you can make a hole, which is really very hard to do, but if you can make a hole from end to end, you're going to end up in the other side of a planet. But if you're accelerating, your acceleration starts to drop because there's less and mass. At some point, there is no acceleration in the center of the Earth. But then because of the inertia, you're going to continue falling, slowing down until you reach this point. At that point, you're going to stop again, and you're going to reverse the process. So this is a continuous oscillation if you were to do this. Again, I mentioned Einstein, actually, and since this is the time for it, Einstein idea is completely different than that of Mr. Newton. How far are we doing in time? We still have about 10 minutes. Okay. Mr. Einstein said, no, it's actually not a force at a distance and a field the way you're describing it. Is actually, there is a space-time, and space and time are both of them, they're connected to one another. And actually, it's not something that is a luxury or conceptual device or something like that. It's actually needed for his theory to explain why light is constant for all observers. But at the end, space and time are basically connected to one another. And then mass, in this case, what it does is it deforms the space-time. It's like your bed, for example. It's well laid out, and you put a big, heavy ball in the middle, and that is basically what the mass does. So now, you don't really need fields the way that Newton has, or forces, The only reason why an object doesn't fall into that, like the moon doesn't fall in the earth, is because it's following a path in here, and that path is the straightest shot basically at that speed. Okay, so this is the explanation of Mr. basically Einstein, and it works beautifully because it leads to some interesting results that Mr. Newton could not explain, like the motion of Mercury. The theory of Mr. Newton explains everything in terms of how fast and all of that, but there was a problem for Mr. Newton trying to explain Mercury. Mercury is too close from the sun to be explained by this thing. So there was a failure then. And Mr. Einstein stated basically the famous basically saying after, if I was happy with that, because there was discrepancy and people couldn't reconcile with it. So they had to include the influence of Jupiter, the influence of Saturn, and so on and so forth, but it's still, there was some odds, a number, small variation. So, but when they included this one, Mr. Einstein, he came up with an explanation for the motion of Mercury that could not be accounted for with Mr. Newton's work. And again, that was a wobble actually. There was actually a motion that is not sitting still in the same orbit like all of the other planets. Jupiter, Mercury seems to move around back and forth, so they couldn't explain it, but now this one can explain it. And again, like I said in the beginning, if all Mr. Newton was able to explain this thing, if Mr. Einstein was able to only explain the motion of Mercury, that is not good enough from him too. We needed something more. And one of the things that came on more, of course, gravity waves that was discovered in 2017, that's another thing, or well, actually before 2017, but there was major hoopla around those times when gravity waves were discovered, before 2017, I should say. I think it's around that time. Anyway, the point being in here is gravity waves that were predicted, and now we have detected them using the LIGO projects, okay? But the other thing also is that actually he predicted the gravitational lensing, something that gravity acts, big massive objects acts as lenses. So if there is a star on the other side, for example, of the sun, and if we can see it during daytime, of course we cannot see the star during daytime, the star will appears to be coming from the two sides of the sun. Sure enough, in 1918, there was a solar eclipse, which means we can see stars during daytime, and we were able to find the gravitational lensing exactly how Mr. Einstein has predicted it. Again, a theory is not good enough just to explain what has been observed, like the path of Mercury going around the sun. It has to go a step beyond. It has to go more than that. Mr. Einstein predicted the gravitational lensing, and sure enough, it was observed. Okay. It was observed. So this is one of the things that was actually confirmation. There were other things too. Like, for example, his theory predicted the existence of a black hole. He didn't like it. He said this is too much of a monstrous thing to even, that nature should not really, it cannot exist. Because if the mass is too big, then for this case, then in this case, if the range starts to become smaller and smaller, so there is a point beyond which that the matter should collapse to singularity. Although that solution was obvious, and it was calculated by Mr. I forgot his name right now. He didn't like that. That's not good. That's not how nature should behave, he believed, okay? Although it's a mathematical solution, but he didn't like it. Sure enough, they were observed later on, okay? So they exist. Not only that, there was another thing that also was predicted by theory later on, neutron stars, which are actually as mysterious and as actually powerful, almost as powerful as black holes also. They are derived from this theory. Again, if a theory just explains something that was observed before, like the motion of Mercury, that is not good enough. Mr. Einstein's theory went a step beyond that, and that's why it's an acceptable theory, and it's impeccable theory, and it explains a lot of things. Among the things that we discovered recently are gravity waves. That was also a consequence. But he also believed that, although the theory predicts them, he said that they would be too small to even be observed. And sure enough, they were observed. We were able to detect them. Okay. Okay, again, black holes are the reason why we call them black holes, and they appear that is because they're basically have super intense gravity, that anything that is going to fall within there, something called the event horizon, it will never come back because of the fact that even light itself gravity is so powerful that light itself cannot escape. Light itself cannot escape. So that is basically, in a nutshell, how black holes are. Okay. So we're dealing with tremendous amount of force of gravity in here. This gravity is so big that there is a tendency in here for it to really make a small, tiny in size probably, but a big dent in the space-time continuum. So it's going to puncture this fabric of space-time. So it's really, they are so powerful. Okay, which brings us to another concept in here, and that is the idea of wormholes. And wormholes, the calculation suggests that if you reach out, for example, in a wormhole, you may be able to tap your back in here. You may be able to touch yourself from the other side, and a past version of yourself or a future version of yourself. Again, because again, this distortion is not happening in space, it's happening in space-time. So you could be basically talking to yourself from the other side. This was suggested as means, by the way. They're quite a lot of energy. They're not easy to make. They are not stable. So if you do calculations, they are not stable. So, but if you can somehow, you could travel tremendous amounts of distances over, keep the time the same. So you could do the other end of the galaxy in a matter of basically a fraction of a second. And that is the idea behind the movie Interstellar. If you guys did not see it, this is a good time to go probably and watch it, because that thing that basically the actors traveled with supposedly was a wormhole. Okay. And that makes an opening from one end of the universe to the other end of the universe, wherever you want it to be, as long as you can control it. This is still a theoretical thing. And at this point, again, it looks like it's too much of a thing to even conceive. But we said that about so many things in the past. We said that so many things in the past, like, for example, gravity waves. Okay. So, and we were proven that we can do that. So maybe in the future, this will be something that we could do. Again, universal gravitation, everything attracts everything. Earth is around because of a gravitation. And again, because there's too much mass pulling on it, and which way the universe is expanding and accelerating outward. That's another thing. Probably we can bring it up some other time. We can talk about it. And maybe we can talk when we do the Doppler effect down the road, and we talk about the electricity and magnetism and electromagnetism and how it is red shifted, okay? When we look at faraway objects, okay? And this is due to the expansion of the universe. Okay, this is your chapter in a nutshell. Again, I'm hoping that to have the material ready. Let me see if any of my other videos from the morning classes are available. Sure enough, they're not, sorry. So again, probably I will send a message to everybody saying that these recordings are experiencing difficulties. So you guys really need to attend the class live to benefit from the lectures, because these are supposed to be regular meet classes, meaning we're supposed to meet when they're supposed to have this ones. No, there was one. That is to explain how gravity works, Jacob. Okay? Through the fields. Objects create fields around them so that planets and other objects, just basically when you put them in there, they feel it. Like the example I gave in here, if I have this rock in here, this point in space has, okay, good, has a field in there. So if I let go of it, now it's going to feel it. So that's basically how gravity works, at least in the classical sense. Okay, guys, I'll see you on Tuesday of next week. Don't forget that the time is changing on this weekend. So make sure you adjust your clock and be on time in class, because again, as I said before, we're experiencing issues with this recording from Zoom. Okay, let me stop the recording for a second.